Yeah, it sounds much nicer. 10 years sounds much better. 10 years plus X, exactly. Yeah. Okay, so I also thank the organizers for giving me the opportunity to talk about this, and in particular, as it's really not a topic which is completely aligned with the major topic of the workshop, but I think this might be interesting for many of you just as a kind of insight into the BSM field and scenarios and so on. Okay, so I have some introductory slides, which are probably not very interesting to most of you, but I think it's still nice to set the stage a little bit. So I will also, is it better to point here or here? Doesn't matter. Doesn't matter. Okay, I point here maybe. Okay, so as we all know, there was the Higgs discovery in 2012, which basically means the last building block of the electroweak sector in the standard model was discovered. So then you can, of course, obviously ask the question, are there any remaining questions? I think the answer is yes, this is pretty clear. So one question is, one can ask is, why is the standard model the way it is? So you can look for underlying principles and symmetries. And this has been extremely successful, this approach, for example, in QCD and so on. So it's really a good idea to think about things like this. I hope it doesn't fall down. Then, of course, you can try to find explanations for observations which are not described by the standard model, like dark matter, the flavor structure, etc. Or you can just take an ad hoc approach and say which other models are still complying with the experimental and theoretical precision. And for all of these, you should look for physics beyond the standard model. And what I've been working on mainly is really testing this in the framework of particle colliders. Yeah. Okay, so now I go to the scalar sector. Why is the scalar sector special? So as you see here, this is the Higgs potential in the standard model, standard notation. Immediately from this and the electroweak gauge couplings, you get within the standard model the mass for the Higgs boson and the gauge bosons according to these expressions here. So everything is then determined in terms of the gauge couplings V and the VEF and lambda. And this form of the potential determines the minimum and the electroweak vacuum structure. Now then, if you continue to think about it a little bit more, this is directly related to the stability of the universe, electroweak phase transitions, and so on and so forth, right? I mean, I think I don't have a plot, but I think most of you know that currently with the top mass at the current value and the best predictions available, we are living in a metastable universe, not a stable one. So this is, for example, something interesting. Now, if I say we have the last building block discovered, it's not completely correct because, of course, we have now all input parameters, but what we haven't been able to do yet is to really test whether also the triple and quartic scalar couplings are exactly as prescribed. And this is not very easy. In particular, the quartic coupling, I mean, is only accessible at really very high energy future machines. So high Lumi gives some constraints. But I think to really build it, one has to look much, or determine or measure this, one has to look much more into the future. And similar statements can be made for the triple Higgs coupling in the standard model. Okay, now if we want to go away from the standard model and we consider now my focus models with new scalar states, this means that you have models with scalar extensions. This is the Lorentz structure description. So you can have many possibilities, which are mainly distinguishable by the transformation properties under the electroweak gauge group. So you can have SU2 cross U1 singlets, doublets, triplets, and so on. What is very important is that there's an important sum rule in green, which I hope you can see, for the additional neutral CP even scalars in the game. And it basically says that for couplings to vector bosons, the sum of the coupling squared of the different, so the sum goes over all CP even neutral scalars. The sum of these squares has to be equal to the square of the coupling in the standard model. This comes from unitarity. If you're interested, there's a really nice, quite old already paper now where this is derived. I have to say, because every time I say this, depending on the audience, someone jumps up and says, no, if you have doubly charged scalars, it's different. So this is true. the sum rule is modified in presence of doubly charged scalars. Yeah. But for most models which have not doubly charged scalars, this is something important because it, of course, we now have measurements for the signal strength in couplings to vector bosons. So this immediately constrains the couplings in the other sectors. Yeah. Okay, so as I said, in principle, there's no limit. You can add singlets, doublets, triplets, whatever you want. You will then obviously enhance the particle content. We'll have additional pseudoscalar neutral, charged, doubly charged, and so on particles. And the common feature is that you have new scalar states, which can now also be produced and decay into each other, and so on. Then the next question you have to ask, let's assume we have this kind of new physics scenario, how can I see it? So there are, of course, a lot of different ways. This is, again, somehow concentrating in the collider or collider and neighbor, so to say, fields. So the first option is, of course, the nicest one in a sense. You see a direct deviation, in best of all cases, a bump or something similar. So you have clearly enhanced rates for certain final states, which are mediated by new physics. So this is this bump hunting by the LHC and other experiments. Then you can, of course, have signatures that do not exist in the standard model. For example, events with large missing energy for models containing dark matter. I mean, this is now not thinking about, you know, missed jets because of detector resolution or very forward events and so on. So I'm really talking about parton level observations, so to say. And what you can also have is, of course, deviations in standard model-like quantities, which are smallish. So loop-induced deviations that require precision measurements. I mean, typically, you know, there are quite a few observables now which are away from the standard model predictions. So G-2, the W mass, if you believe the CDF value, but even without the CDF value, there's a discrepancy between standard model prediction and measurement. So, okay, so this would be the third option. And when I say small, these can also be large because you know that as soon as this W mass measurement from CDF came up, suddenly there were billions of models which were able to explain it. So I would call this a not so small deviation. Okay. Now, obviously, I cannot cover all models and all new physics states and so on. So I'm kind of trying to concentrate A, on popular models, and B, on things I did. So this is category A, 2 Higgs doublet models. I didn't do so much on this, but it's a very, very common extension. So what you do is you have you extend the scalar sector by one additional doublet. In principle, this can lead to flavor-changing neutral currents. In order to prevent this, you introduce additional symmetries in the potential, and then this is the particle content. So you have 2 neutral CP even scalars, 1 CP odd neutral scalar, and then charged scalars. If in the most minimal version, all these symmetries applied, then the parameters are masses. Then tangents beta is the ratio of the VEF of the 2 doublets. Then this is a mixing angle, so basically alpha, which is parameterized in this cosine beta minus alpha due to some limit properties, is a mixing between gauge and mass eigenstates in the CP even sector, and an additional parameter in the potential. So this is subject to a lot of constraints, not only collider, but B physics, then of course direct searches, signal strength, and so on. And typically there are 4 different types discussed most frequently. So these have different Yukawa couplings, and this leads to different effects of the constraints, in particular in B physics, but also for direct searches. Now I was trying to look for a nice example, and unfortunately, really the one I found is already a couple of years old, but this is, I think, still a very nice plot. This is, of course, not the latest up-to-date result anymore, but what you have here is the mass of the heavy scalars, then this tangents beta value. You have type 1 and type 2 couplings in the Yukawa sector, combination of various direct searches. And I think what is quite, I mean, the only thing I want to say, I don't really want to discuss why is this wiggle here and so on, but what is really interesting is that you see that several searches are really complementary in both scenarios. So they kind of cover different regions in the parameter space. And that also, it really depends a lot on the type of 2X doublet model you're looking at. So you have some regions here which are excluded, heavily excluded, for example, by this tight tau final state. And here this is still allowed. Yeah, so this I think is just a very nice example on how different searches by the LHC experiments cover different regions of parameter space in such models. Okay, then another very important thing is this, or very important parameter is this cosine beta minus alpha. So if this goes to 0, this is called the alignment limit when you're back in the standard model, in particular for gauge boson couplings. And this is, I think, the most up-to-date constraints from the Atlas collaboration. It's still not published, but this is full run 2, if I understand it correctly. Yeah. And you see here again for different types, I think 1, 2, and then, okay, 2 other ways to couple the Yukawa couplings. You have constraints. The most important message is that we are really very close, very, very close to the standard model limit. I mean, here there's some space still, but this cosine beta minus alpha is really strongly constrained by now, and this is only signal strength. So this is inferring from the signal strength measurements of the standard model-like scalar, which of course also scales with something with sine beta minus alpha, and you really see that you only have very small regions which are still allowed. So the next question is then, this was one particular model, and then you can say, how does it work in general? And here I took some slides from last year's Higgs working group meeting, so I have to say they are slightly outdated, but again, they work nicely as an example. So they were prepared by my co-conveners from Atlas and CMS in the extended scalars subgroup of the Higgs working group. And this, again, now you're not supposed to understand each little wiggle and so on, but it just gives you a kind of survey. What are the, by that time, hottest results? I mean, I didn't update this with new results from EPS and so on, but in particular, I also have to say there was nothing that surprising now where one can say this is something you really have to show. Okay, so there will be 2 slides from Atlas, 2 from CMS, and again, for different models, again, you don't have to understand everything. So the first one here is again such an overlay plot like I already showed. The one before was, however, from theorists. This is now from the experiment. So there's a scalar mass here and the mixing angle, and there are various searches. It's maybe a bit too small to see, maybe even for me, I have to say. And also here. Okay, I'm sorry. So these are various searches in diboson final states, mainly for this Georgi-Maciejczak model. And again, you see that there's a large region which is excluded by complementary searches. Then there were new results for this TTA-H. So TT bar associate production of a heavy scalar to TT bar final states. So my understanding for tops in the final state, which gave new results, which apparently have not been done before. And again, here there are some search results for 2 Higgs doublet models, again from various search channels, where you again can see that various searches constrain various regions in the parameter space. Yeah, for different type. It's both type 1, but it's different settings. Yeah. Okay. Another Atlas discussion here was the H and WH, so diboson in the vector boson H associate production. So this is again something which can be realized in many BSM scenarios and can be also mediated by different intermediate states. As you see here, for example, you have a similar final state, but here this is mediated by the CP-ODD 2 Higgs doublet model scalar. And again, you just see that this is, I mean, here there's still this alignment region allowed, but most of the parameter space is forbidden. One has to be a bit careful here because very often some of the parameters are really set. So this second mass here is set, for example, tangents beta is set. And as soon as you open up the parameter space, you let these float, so these bounds can or cannot apply anymore. So by looking at plots like this, one should not say it's all excluded. It's excluded if you take these particular values for some of the other a priori free parameters of the model. And then there are some additional searches here. Again, this is a similar topology, so gauge boson and heavy scalar with additional decays, which was new by that time. And that's again an A to the H search. So I think the message from this is that really people try to discover or look at all possible signatures which are allowed. I also frequently ask to provide new signatures which are not yet investigated. And unfortunately, so far, most of these searches really point to standard model-like scenarios. Oops, I was too fast. Okay, then CMS, they also prepared some slides for us last year. So yeah, this is here a scalar to tau tau final states, some new results again, which you can then interpret in a certain 2 Higgs doublet model. Then in the MSSM Higgs to WW, again with a certain interpretation in the parameter space. And then here, this is something which is relatively new. I mean, not anymore so much, but results start to come out. So what you have is you have scenarios with 3 scalars, which all have different masses. So for example, here you have this X, Y, H. H is in this notation, the standard model scenario. And then you can also provide basically limits on the production times decay branching ratio in the 2-dimensional mass plane, color coded here. And here you see some constraints in the NMSSM and the TRSM. In the TRSM, I know because I've provided these bounds. So what we did is we provided within the model maximally allowed cross section. So again, it doesn't mean that these models are really excluded here. It means that the search is sensitive to some region of the parameter space. Yeah. And on the right, you have charged to neutral and W, and the neutral scalar goes to tau tau. So this is again a new signature which has been presented last year. Again, as I said, I mean, these are examples, so this doesn't mean that this is the newest up-to-date thing, but this was selected as the most important in last year's discussion. Okay. Then I briefly want to mention what happens if you go away from only looking at collider searches, but you also kind of combine it with other constraints. And a very good example are flavor constraints. So typical example are 2 Higgs doublet models, where you have constraints in the charged scalar tangent beta plane. This typically sets lower limits on the charged mass. And then the charged mass in 2 Higgs doublet models is then strongly correlated to other additional masses via the electroweak precision measurements. Yeah, so you cannot have too large gaps in the heavy sector, otherwise you get a problem with STU or electroweak precision. So this puts then a lower bound on additional scalars. Yeah, and this sounds first okay. Whatever, it doesn't matter so much, but if you then say, let's now look at E plus E minus colliders, what can we investigate? It means that for certain new physics scenarios, you really need TEF scale center of mass energies, and they will not be accessible at Higgs factories, for example. So I will show very briefly some example I worked on, but again, not taking the latest constraints into account. So this is a typical plot, tangent beta, and the charged mass in this 2HDM plus A, which basically behaves like a 2 Higgs doublet model. So I have this B2 XS gamma, which basically sets this line here. This was something which was provided to me by Nikolai, nicely enough. And then you have ds to mu mu and delta ms. I did via Sphino. And you see here the most important thing, the red points are allowed. And the most important thing is that you have a lower bound on tangents beta in this scenario. And this is what I just talked to you about before from STU. So here again, what you see are all points I generated, all points. The greens are forbidden, the red ones are allowed in this mass difference plane. So here charged versus minus CP even neutral, charged minus CP odd neutral. And you see that you cannot go too far away in the degeneracy here. And on the right-hand side, I plotted something similar. So this is again charged minus CP odd, and then here the 2 neutral ones subtracted. And I plotted basically also the difference between this 2HDMA, which has an additional CP odd, second CP odd neutral scalar, and the 2 Higgs doublet model. And you see, as expected, if you add more particles, then the bounds become relaxed. So this was a cross-check. STU, the oblique parameters from Peskin and al., where you have, yeah. I mean, it's the, yeah, it's electroweak precision. Yeah, I mean, it's G-fitter, right? So they put in whatever they have from a large number of experiments. Doreen knows much more than me about this. I mean, there's a large number of observables, and then you, under certain conditions, you can parameterize it in these 3 parameters, and G-fitter gives you some values for this and correlations, and then you do these bounds. Yeah. Okay. This is basically what I said for this particular case. For example, this HA channel is only accessible for 1 TeV or higher platonic center of mass energy. And this is something many people seem to forget, because you have a lot of studies now also for 2x doublet models with lower masses. And one always has to be a bit careful. Okay, then I jump. I don't know how much time I have. I jump briefly on this multi-scalar production mode. So this is something I've been working on a lot. So the idea is that you have in total 3 CP. Thank you. Very good. Now I know. I can talk very slowly now. Very good. So you have in total 3 CP even neutral scalars. And you can think about various production and decay modes. So, for example, what we are thinking about here is the H1 is the 120, the heaviest guy is the 125 GeV particle. Then it decays to, this is this asymmetric here, then it decays into 2 particles which have different masses. This can then decay further into 3 lightest scalars, and this is just the branching ratio of the 125 into these 2 additional scalars. You see some exclusion bound here. This comes from the signal strength, basically. Yeah, and this is just a general idea. So you can go up to 7% in this. Everything else is excluded. Then if you go to the right, what happens here is that the lightest scalar is the 125 GeV scalar. So you have 2 heavy masses, and again, this asymmetric production heavy scalar goes to 2 different masses. One of them is the 125 GeV. And what is interesting here is that really, I mean, this form was the original plane we proposed in this very first paper. And now already quite a few searches, especially this new asymmetric search here, has excluded, I know this is the Higgs to ZZ, sorry, but there's also an asymmetric search here, which really has started to exclude this parameter space. And these little dots, I still, if I have time, I can talk about them in a second. These were points which we investigated for 325 GeV final states. Then there are also decays where you have a heavy scalar going to 2 lighter ones, but none of them is the 125 GeV scalar. So this is one plane here where you have production cross sections up to 2.5 picopan. This is the log color coding. Sorry, I didn't write it apparently here. And you see that there's a large region. Some of them are already constrained by Higgs searches. Yeah, this is quite interesting because the resolution is too bad that you also go down to relatively low masses here, which are not at 125, but still excluded from this search. And then on the right-hand side, my favorite plane is that we have 2 light scalars. One is reduced decays and 2 even lighter ones with really cross sections. Okay, up to 60 picoban, but this is in this very low mass range here, which I don't really believe the bounds so much, but you still can get relatively large production cross sections. So this is quite nice. So this benchmark plane 3 is the one where you have this asymmetric decay. The H2 can go to 2 H1s as soon as you open up the parameter space. So the kinematics, this is the same plot I showed you here. These are the branching ratios as a function of this second mass. And you see, as soon as you're above 250 GeV, you open up really these channels. The most dominant decay is then 4 Bs, 2 Ws, then you're followed by 6 Bs, and so on and so forth. So this is something where these cross sections are much larger than the standard model triple Higgs cross section, and this is now starting to be investigated by the experimental collaborations, in fact, in great detail. So we did a Pheno study also some time ago with Andreas and Gilberto, where we concentrated on the 6T final state. We selected some points, which I showed you before in this benchmark plane. Okay, we have a full top-bottom mass dependence at leading order using some UFO-Metcalfe-Herwig interface. We also used K factors when appropriate. And I'm not going through all the details. What is important here is that we have here these 2 masses, 2 additional masses, then cross sections before decay, after decay. And then after a longer selection study and so on, these are the significances. You can have a 300 inverse femtobarn or 3 inverse attobarn. I mean, of course, this is something which should be cross-checked by experimentalists, yeah, whether all our assumptions in the analysis are justified or not, but I think still this gives a nice impression, in particular because this is basically, if you would combine run 2, this is where we are now, no? 300 inverse femtobarn, so this would be already quite good. Very briefly, something I've been working on now with Elina and one of her master students from Hannover is to look at finite width effects in these Higgs searches. I mean, they are already discussed in the literature, in particular for Higgs invariant mass distributions. However, somehow this always gets forgotten. So every second time there's a talk, people are surprised by these effects, although they have been in the literature for 10 years nearly now. So there's a scenario I'm discussing here. Okay, you don't really have to look too much in the details. What is important is that you can say instead of the full cross-section, I add, without the interference term, I add these two terms where I say only look at the resonance and I look at the kind of standard model-like contribution, and then you have some interference here, which in this scenario is 3 femtobarn, which is not super large, but still also not too small. Oops, it was too fast. So these are the results. We also plotted now for the first time the PT of the Higgs. So this is the typical plot, the Higgs invariant mass in this scenario. The blue line is what you get if you do everything correctly. And the green is what you get if you add them up incoherently without the interference. And you see this typical structure, which has been published a lot in the literature, that you have this peak dip structure here. So you have a dip here, which you do not see if you do the calculation wrong. Yeah. And then we also said we can look at this for a certain integrated luminosity. So this is for basically 140 inverse femtobarn, just to see will this be seen due to statistics. So then you have the difference here is the green line, and then the blue contour is basically just a square root of n, so statistical effect. And you see that you really do have a large effect here. And the PT of the Higgs, I think this has never been shown. I haven't seen it anywhere so far. It's the same discussion. So you have the blue line, which is the correct description. You have the green one, which is if you add this together, and again, you have the difference here. In this difference plot, there's a larger discrepancy. In fact, there's a large discrepancy here. There's also something in the peak, but this is maybe not so important. But again, I mean, the logic here is always, what if you train your neural network, for example, on the green stuff, but the blue is what you really get, then you cannot really say that you're looking for this model, because you look for something else where the interference doesn't exist, which I cannot imagine where it should come from, but okay. And this is a debate, yeah. I mean, some of the experimentalists refuse to include the interference because they say it's model dependent, but then you say there's no way you do not have the interference because it's mainly the one with the 125 and the top box. And this is always there, independent of your model, yeah, if you have a second scalar. But still the discussion now in the Higgs groups of the experiments is whether or not to include this, which, okay, I leave it like this. I'm also too fast. Again, so just briefly at Higgs factories, of course, you also can think about extra scalars, in particular in this scalar strahlung, so to say. These are production cross-sections for a standard model like scalar at 250 GeV with Metcalfe leading order as a function of the mass, and you see that you go up to 0.5 picobarn, and then you go down depending on the mass. I didn't look at you because I don't know what you showed me. Yeah, but now it's 5. Yeah, at some point you showed the 10, but I don't know how long ago. Yeah, so okay. Anyway, okay. So what I also plotted here is you have the ZH, and then people also say, we have this VBF type signature, right? So E plus E minus to nu with a Z with the W's and the W going to the H. But then, of course, from the ZH you also get this final state, right? For the Z splitting to 2 neutrinos. So this is what I plot here in the green line. And you see that at low center of mass energies, you do have a contribution still from the other topology. But if you go to higher masses, basically everything from the neutrino Higgs comes from the ZH and then Z going to neutrinos. This is, of course, okay, I mean, you cannot really apply VBF cuts because how do you cut? You can in a sense, but Anyway, I think the message here is that if you look at the first back of the envelope discussion at CH only, this is already fine. Now this is for standard models, so due to the sum rule, you have typically rescaling of by 10%. Yeah, okay. Then again, I looked at this model with additional singlets, folded, applied all bounds, and this is really recent. So this is from 2 days ago. So everything which has been available in public tools, I didn't do a recast of all analyses, but in public tools has been included here. So you have here the second mass, you have the cross-section femtobarn at 250 GeV. And you see that you can, in particular in this range, you can go up to relatively high cross sections. Then you can also say what would be the dominant decays. So you see here a large fraction is of course BB bar. You also have additional Higgses. So this would lead to a signature of a Z and 2 light scalars, yeah, which further decay. So for example, a Z and 4 Bs also. And you also have some tau tau and CC here for very low masses. And these are the cross-section, I mean, femtobarn cross-sections, so I think it's not so bad at the moment. Then the last topic is that people have also looked at the CH production with the H going to 2 scalars, which further decay into jets, Bs, and so on. So this is a kind of paper which is referred to by everyone now already some time ago, 6 years ago, where these people projected in a Spheno study kind of gave upper branching ratios for these various final states in this scenario for 240 GeV. So this was CPC, I think. And also for the BB bar. And many people are using these lines now in their models. So they don't do a detailed study, but they just use these projections. So this is an example I show you here. Because what can happen is if you have this additional light scalars, you can have a priori a strong first order electroweak phase transition. And I'm not an expert, so please don't ask me about the details. What is important here, for example, is that you have the second scalar mass, the lighter one. Then this is a limit on the production times branching ratio divided by the standard model production cross-section, I guess. Yeah, exactly. And what is important is that this blue band here is the region which, according to these authors, provides a strong first order electroweak phase transition. Then you see various, by that time, projections for discalar searches, light discalar searches. And you see here these projection lines, which are coming from the paper I just showed you. And just the difference is different projected luminosities, right? Okay, so this is something which is always shown now for Higgs factories, that you can, in principle, with the precision you have in Higgs factories for these final states, that you can then exclude and or confirm a model with a strong first order electric phase transition. Yeah. Okay, some promotion of something which is ongoing. So there's an ongoing ECFA study, direct discovery potential at Higgs factories, and I'm part of this extra scalar. I didn't do anything. I don't do anything. Something happened. Oops, something. It's blinking there. Did you do something? No. Okay. Some magician did something. Very good. Okay. So there's an ongoing ECFA study, direct discovery potential at Higgs factories. I'm part of this extra scalar subgroup, and why I'm mentioning this is that we have set up a document which should have already been available on the archive. It's okay, as usual, delayed, where we and the other subgroups, I think they're like 15 or so in total, specify processes which we want someone to study. I have to say it like this because we cannot do it all by ourselves, and the idea is to have then something which goes into a white paper or yellow report, which then is input for the next European strategy. So we specified these two main signatures, E plus E minus. This is the scalar strahlung. The BB bar is the typical one. Tau tau now has been started to be worked on by Philip Janecki in Warsaw, but there are a lot of different additional final states one can investigate. And the second one is what I was just talking about, the 125 to 2 lighter scalars, which decay further. And the reason for this is that we said it's very nice. There's a Pheno study from 2016 or 17. However, this is really the paper everyone cites, so one should maybe scrutinize this a bit more in more detail, and also for different decays. So please read this, yeah, and let us know exactly. And okay, that's it. So I think models with extended scalar sectors provide an interesting setup to introduce new states with different CP and charge quantum numbers. There are many new interesting signatures. Some of them are not yet covered by current searches. So I also have to say, in our extended scalar subgroup of the Higgs working group, we are currently looking for novel signatures, but this doesn't mean, the same signature was already investigated in a new model, but really something which so far is not looked at by the experiments, because otherwise they will probably refer you to their older searches or say, please do a recast, or convince us why we have to redo the search with a different model interpretation. And then, of course, inside of the European strategy and probably also SNOMA's outcomes, to reinvestigate this at the plus and minus colliders. Okay, that's it. Yeah, many topics.
Questions for Tania? Okay, so let me.
Okay,
there's
a question over there, but
there was one.
Yeah, curiosity, but of course, you realize I don't know anything about this, so forgive the naive question.
A little bit.
When I think of extra scalars as well as other part, I naturally think of heavy stuff. But now you pointed out about an interesting possibility of Higgs decay into light scalar.
Yeah.
How much room is there for light scalar? Shouldn't we know already?
I think there's a lot of room. Now I cannot go back anymore. So, yes. So this, for example, the bounds you see here, this is mainly coming from lab. Yeah. Most of these are lab searches still, although there are these, I didn't show it here, maybe I have it in the appendix. There are some constraints also from direct searches from the LHC. The problem is that typically they go to BB bar. I mean, BB bar is good, but still you have relatively low rates because of everything being mediated by Yukawa couplings, right? So, okay. But in principle, this is now for this TRSM model. You can also look at the decoupling where you only have one additional light scalar, so there's still a lot of room.
But how should I read this? So the cross section is smaller for very light, so we have less of a bound for if they are lighter. And there is more room for a 20 GeV scalar than for an 80 GeV scalar. Is that what? There's
less room, right? I mean, it's less allowed, and the reason is that you have strong constraints from the 125 to invisible or unknown. Or now they distinguish this, but I mean, this is the 7% I also showed.
I was reading it.
Yeah. So I think the official bound now is 11%. But this comes from direct Higgs to invisible. But if you use a fit, it will be constrained to 7. And the fit comes from signal strength. So the signal strength basically allows for 7% of undetermined decay rate. Yeah. And this hits in as soon as the lighter you go, the larger this gets. I mean, you really have to fine-tune the coupling to the 125. So this is why in general scans, if you have models with this very low masses, they are typically completely excluded unless you really zoom in with the knowledge of what you have to do in order to be okay. But there's a lot of room for these things, yeah. And what is also not investigated to my knowledge is, for example, direct production of these things at the LHC. I mean, they would be large, yeah, large cross-sections, but
so maybe for this workshop, I haven't followed this for a while, but what is your feeling in terms of the tools used to put constraints by the experimentalists from the theory side? So is this still Mudgraph, Trust is something? So in terms of position of how you model these new physics signatures, I mean, that has an impact on the constraints they extract, right?
I think the major efforts there, I mean, I'm not the right person. Michael Spierer should stand here and give you the answer. He will give you a very long, detailed answer. So, okay, I mean, to my knowledge, most of the searches or the model interpretations are leading order, maybe with a rescaling of the total cross-section. This is my understanding at the moment, yeah. And I can also understand it, because even if you have k factors of 2, you might be off by a factor 2, and then the line is shifted somewhere. Yeah, I think these things this is my personal opinion, become important once you have something. Yeah, but even then people do all this leading order for this apparent deviations. They do leading order fits and so on. So where it is really important are the branching ratios. Yeah, so all the ones. So we are now collecting recommendations for the 13.6 TeV center of mass energy for production rates. I mean, as somehow part of our task as conveners, and these are all done to the highest possible order. Yeah, which means NLO for sure for all the production of charge scalars, for example, and so on, and also the decays are from HDK. So whatever orders in HDK is included in the proposed or recommended branching ratios. Yeah, but for simulation, it's a time question. Yeah, I mean, even if there were dedicated one loop Monte Carlos for BSM for the charge, I mean, for the this is all not colored, right? So you have a global production K factor, which you can basically take from the production. And then the electroweak effects are not large enough. The only exception is really the under 25, I mean, the Higgs mass in the Twix doublet model, which you need to have at 2 loop, because otherwise you're below the Z mass, I think, which is excluded now somehow. So, but apart from this, yeah, I think, I mean, even if you do a pheno study yourself with whatever best tool you have available, the experimentalists will tell you we are not going to use it. It takes too long. Yeah. I think.
Okay.
I mean, we tried to convince them already of this finite width, which is leading. I mean, it's a higher order effect, but it's a leading order Monte Carlo, and this is already difficult to convince them of. So, yeah.
Is it the same what Nicholas Kauer already discussed?
500 years ago. Yeah, I agree.
It's still.
Yeah, people forget it. This is the problem. He started talking about it. They do something else now in this width subgroup, and now, in fact, he also got out of the group as a convener. So I really had experimental conveners for Higgs not being aware of this thing, and this has been done by Sally and Ian Lewis and so on, and Jen also a long time ago, in fact, right? So one has to repeat it infinitely in order to land somewhere. So our hope is with this interference paper, once it's really documented, not only for one distribution, but for several PT, I mean, we looked at various observables, then maybe it starts to register. Are there really large effects? One has to think about it. Yeah.
Okay, yes, I'm coming.
I have a curiosity concerning, you showed the slides where you show Higgs strahlung at E plus E minus collision.
For E plus E minus.
Where you show the Z decaying into neutrino.
So yeah, I know this. No, it's the wrong direction. This one.
Yeah. So it's a general curiosity. Because of this Z decaying into invisible, essentially, I would expect that in this kind of measurements, effects related to initial state radiation of QE origin could play a role. So I was wondering, how does uncertainty in this modeling impact this measurement, and maybe how the situation will improve if you ideally go to a muon collider, for example.
Okay. Muon collider is not difficult because not important here. But like this, quasi massless electroweak gauge bosons and so on. So I think from there are studies. I mean, this is very nice. Maybe I have to check out. I typically have a plot from Jenny List and friends for, in fact, different detector. proposals, ILD type 1, type 2, whatever. And they did a simulation for this lighter scalars, and I think it's the recoil method, which means you're not thinking about the decays of the Higgs, but you just look at the Z recoil. And I didn't look at the paper, but knowing Jenny, she did the best one can, yeah, which means initial state radiation, beam spectra, etc. pp. Yeah, so the lines, what they show are lines, but I think if you look, I would assume if you look into their paper, you find some statements about this. But I think, I mean, at the moment we are trying to convince people to build this, right? This is the political message, so to say. I mean, or whoever we is. But so these things are interesting. There's a lot of discussion of higher order in the standard model sector for E plus E minus. Yeah, for FCCE, I mean, precision calculations for the Higgs ZH and electric gauge bosons and so on. But I think for BSM, it's always below 10%. Yeah, so. Yeah. What is important, however, of course, is this radiative return. This one shouldn't forget, and this is a huge effect, right? When you allow from ISR, you allow things to run up, basically, the production cross-section. So this, I think, is important. And none of this is MetGraph. No, none of it is included there. Yeah.
Okay. Any other questions for Tania? No? Okay. Thank you very much, Tania.
Yeah.